My name is Leen Govaerts. I'm heading the research department on energy and water transition at VITO and will be your moderator today. In global energy transition, we often look at the sun and the wind, but beneath our feet lies a powerful, stable and vastly underutilized source of clean energy, the heat of the earth itself. Today we have a very fine lineup of experts who will take us on a journey across the globe and across the value chain of geothermal energy in 4 concise presentations. We will start by understanding the immense potential waiting to be unlocked in new regions like South Africa. And then we'll learn from the real-world experience of a global leader in geothermal energy in Kenya. And from there, we will deep dive into a cutting-edge technology that is making geothermal more efficient. Finally, we will peer into the future to see how geothermal can be integrated with storage and solve modern challenges. So I'll invite each of the speakers to the stage. Each speaker has 20 minutes to share their insights. We have a strict schedule today, so I will be strict if you are about to exceed your 20 minutes. So as a first speaker, I would like to call Moussarat Safi to the stage. She has evolved from mining to the research sector. Her expertise in geology was honed through hands-on experience in the exploration and mining industry, where she spent time in mapping, drilling, and project management. Transitioning from fieldwork to laboratory research, she utilized mineralogy, chemistry, and metallurgy to deepen her geological knowledge. This shift allows her to bridge the gap between ore processing and practical application. Recognizing the importance of energy in sustainable operations, she expanded her focus to include energy resources and landed into hot water. Her interests are in research and minerals and energy industries. Please, Moussarat, the floor is yours.
Good afternoon, everyone. As Lynn has introduced me, I'm going to try and show you the journey, how we've unlocked geothermal energy at the Council for Geoscience. This information is only for you, and any reproduction of this information is not allowed unless we give written permission. My talk will go through acknowledgements, and then we will look at the results first, because sometimes we only have 2 minutes to have the attention span, so I'll give you the results, and if you don't want to listen to my talk after that, that's fine also. And then we will look at the South African context of where the energy is, and what is geothermal energy in South Africa. Thereafterwards, we will go and look into how we unlock geothermal energy in South Africa, with some materials and methods, results, and then I'll go back to the results, and then the take-home message. Firstly, I would like to acknowledge all the privately owned, municipality-owned, community-owned geothermal waters, areas where they allowed us access to work in the areas, and also to the management of Council for Geoscience and all of the staff members who support me in many ways to achieving this goal. So when we think of geothermal energy, we think of enthalpy. When we look at enthalpy, we look at low enthalpy ranges. I don't know if you can see my pointer. Okay, there we go. So we look at low enthalpy ranges, which is from 4 degrees to 95 degrees, and that can be used for, that can be used for heating, cooling, drying, and in the food industry. While traditionally power generation works with enthalpies that are higher than 852 or 204 degrees higher. But as technology evolved, we are able to produce power with enthalpy ranges from 95 degrees to 204 degrees. And with this in mind, we predicted the temperatures of the waters in the black dots, and we found out that there are 20 sites that are potentials for geothermal energy to be used for power generation. And with that in mind, we use the temperature to predict the depth of the geothermal waters. And we have found that the depth is between 1.5 and 3 kilometers. How did we get there? So let's talk about the South Africa's planned energy generation. When we look at this graph over here, we look at in 2018, there was 89% coal, and at this moment we are using 70% coal to power, to produce energy. And in the next 5 years, we want to decrease our coal power generation to 55%, all the time increasing renewable energy in the country. But in this integrated resources plan, geothermal energy does not feature. Maybe we should wonder why doesn't it feature? When we think of geothermal energy, we think of hotspots, subduction zones, and active volcanoes. But this is absent in South Africa. Yet we have hot springs or geothermal waters in the country. Let's take a look at where they are located in the country. So this map shows you all the different geothermal waters that we had sampled in the country. There are 41 sites. And we looked at the geological regions of the country, with the light blue being the Kaapvaal craton, which is the Archean basement, which is a stable craton, and it's overlain by volcano sedimentary formations. It's also, the geothermal waters also occurs in orogenic belts like the Limpopo Mobile Belt, as well as the Cape Fold Belt in the south of the country. As much as we can see that these geothermal waters occur across the country, let's see what they look like, some of which I jumped into hot waters, I literally did. And then one is at Remfasmark in the Northern Cape. This geothermal water surfaces at 38 degrees hot. We have another one known as Chippies, which means something hot. And it's in the Limpopo province, which is in the north of the country, and it surfaces at 54 degrees hot. This is one of the hottest. And then we have another hot water that is called Brandvlei, which is a burning pool of hot water, loosely translated. This water surfaces at 62 degrees hot, and sometimes it also goes up to 100 degrees in summer. But what is the geology of these geothermal waters in South Africa? Let me take you through that. So we said we have the Archean basement, and then we have volcano sedimentary sequences that overlie the Archean basement. And as it rains, the water gets infiltrated further, deeper underground, and through fractures and faults, it travels further deeper underground. And as it gets deeper underground, it gets hotter, and with pressure, it needs to ascend to surface, which use, again, fractures and faults to surface. The heat from underground is either from the magma, or there's radioactive decay of minerals such as uranium, thorium, and potassium. And then when it surfaces, we have hot springs that we see on the surface. Now, how do we unlock geothermal energy in the country? We've done the preliminary survey where we looked at the different hotspots in the country, and we've seen where they occur already. At the Council for Geoscience, we're looking at the exploration part of the geothermal, where we actively sampled all the hot springs that we could, and we did some geochemistry and some geophysics with temperature gradient. The one that we did not get to was heat flow maps. On your right-hand side, you see us doing exploration, and myself in the middle here, where I've been to Chippies to sample the waters as well. So what does exploration mean in terms of geothermal waters? To unlocking it, we did hydrochemical sampling, where we had to engage with stakeholders, we had to do field planning, and we had to ask for access to some of the geothermal waters. As you can see, some of it was denied, but most of it we got. We had 41 sites that we sampled, and the final result is where we did various chemical analysis to get the hydrochemistry, the chemical geothermometry, and the thermal storage and the reservoir depth. With this in mind, with hydrochemistry, we look at what are the concentrations of ions in the geothermal waters, but that gives us an idea of when the waters ascend to surface, we have an idea of what water-rock interaction has taken place. So in that sense, we took the chemical geothermometry is where we take the concentration of different cations and silica, and we replace them into these various equations. There are 14 of them. I know you cannot see them because they are so small, but I would just give you an example. For the one, silica forms in different forms like amorphous silica, chalcedony, cristobalite in different forms. So that's why we have various silica geothermometry or equations. And then we have something called sodium and potassium geothermometry, where we substitute the sodium and potassium into the equations to predict the temperature. After that, we also looked, because we could predict the temperature of the water, we decided let's see how deep it is. And how we did that is we used the predicted temperatures minus the ambient temperature divided by the geothermal gradient, average geothermal gradient of the area. Okay, with the chemistry in mind, I would like your attention on, this is called a Piper plot, where we looked at all the chemistry of the geothermal waters. We have sodium chloride waters that occur in deep, ancient, and marine environments. And then we have magnesium carbonate, which occurs in deep groundwaters. We have mixed waters, which occur in deep groundwater, together with, it has been influenced by ion exchange and shallow waters as well. So let's look at the silica geothermometry, means the prediction of temperatures of the reservoirs underground. We use the various equations on the right-hand side. We substituted the silica concentration for each of the 41 sites to get the temperatures of the water, the predicted temperatures. We can see that the highest temperature is 240 degrees, and there are some that are even lower than 0 degrees, which is not possible because the geothermal water surface is higher than 0 degrees. The measured waters are around between 30 and 50 degrees, and some of them are a little bit higher, like Brunfley, which is 62 degrees. We did the same thing with the cations, which is the sodium, potassium, and magnesium concentrations, and we plugged it in for 41 sites again to see what the temperatures are. We have the highest at 550. Then we have some that are even lower than 0 degrees, which we did not take into account. And then, as you can see, the measured temperature with the green bar shows that the others are possible. With a lot of experimentation, we decided to go with, I don't know, okay. So we correlated the temperature, the predicted temperature using the quartz geothermometer, and then we correlated that to the enthalpy range using the Henle table. And this is what we got in the end to see what is viable for power generation. So we have all of these sites, 41 sites, and we decided to use the temperature and then show you the depth of how deep the reservoirs are. I just want to remind you that the low to medium enthalpy range is between 419 and 852, which can be used for power generation and many other uses, but we were looking at power generation to see. With that in mind, we had 20 sites that we could use for power generation, potential power generation for the country, which is 1.5 kilometers deep and between 1.5 and 3 kilometers deep. Where are they in the country? I tried not to put the names of the potential sites because this is still a study and it's infancy stages. So you can see that in the geological sense, it occurs in various geological regions across the country, from the north all the way to Cape Town in the south. And the take-home message, we have 20 sites that are potentials to use for power generation. By utilizing the geothermal gradient and the geothermometry, we were able to see that the reservoirs are between 1 and 3 kilometers deep. And the next step is to do feasibility studies on one site or many sites, depending on how much money we get. And that in mind, remember I said that we did exploration. Our next phase is test drilling, where we have to find a site that we can drill into the reservoir and do a lot of tests on that in terms of laboratory measures on cores, cuttings, geophysical logging, and so forth. But at the Council for Geoscience, we have a method in the geophysics called magnetotellurics, and we are able to image the subsurface using electric and magnetic signatures. And we are able to find out how deep the reservoirs are. We've done that for 2 sites already, and the geothermometry matches up with the geophysics data. And that in mind, the last point is geothermal energy worth it in our country? And we look at the average prices of coal. How much does it take to produce power? For coal, as you can see, is 195 cents, South African cents per kilowatt. And then we have concentrated solar power, which is 474 cents, compared to the global cost, which is 74 cents. And then when we look at geothermal energy, because we don't have it in the country, we couldn't cost it. But it's sitting at 103 cents. It's a quarter of the solar power to use geothermal energy. And with that, I thank you for your time and your attention. Thank you.
Thank you very much. I could ask many questions about the equations, which I fully don't understand. But what would interest me is, have you already kind of an estimate how much of the power production geothermal could give with this potential? Or is it, you had a calculation of the cost, but do you say we can go to 5% of electricity production for the South African demand? Or is this do I need to come back in 5 years?
We have done, it's not working. Okay, we have done pre-feasibility studies on 2 sites, and we have looked at how much of power we can produce with what we could find at the moment. So it was like 1 megawatt power plant or a 5 megawatt power plant, and the cost is between 1 and 3 rands of South African rands. Yeah, so it just depends on. Also, we have to look at the rate of extraction of water and to ensure that it's sustainable instead of extracting a lot and then we don't have anything left over. Okay. Yeah, so that type of thing. Okay. Thank you.
Thank you very much. So then I would like to go to the second speaker, Mr. Cyrus Karinhiti. He is a geothermal energy technology and innovation expert with over 36 years of experience in developing renewable energy systems across the East African Rift. His landmark achievement was at Kenya Electricity Generation Company, where he led the Olkaria geothermal project, overseeing cross-functional teams over 300 professionals to expand Kenya's geothermal capacity from 45 megawatt to over 800 megawatts. This involved managing the drilling of more than 300 wells and executing billion-dollar projects from conception to completion, all following due standards, ESG standards, and so on. In July 23, Cyrus brought his extensive expertise to the Fortescue Future Industries, where he provides technical leadership in developing frontier technologies like green hydrogen, ammonia, and fertilizers to decarbonize industry. As a seasoned leader, he is skilled in engaging with international financiers and integrating innovation such as artificial intelligence into energy transition technology to advance sustainable development goals and improve community livelihoods. We look forward to your talk, Cyrus.
Thank you. Good afternoon. When I was growing up, we didn't have electricity. So I took it upon myself to make a difference in our community by making sure that other children can be able to have electricity as they grew up. This is a satellite map of Africa at night. Thank you. Thank you. This is a satellite map of Africa at night. And as you can see, the continent is still dark. And 60% of the population have no electricity. So for the investors in this room, that means you have 645 million new customers. So if you were to provide one solar panel to each of those customers, you may not require to look for any money until kingdom come. Now, if Lynn, our moderator, had 1 megawatt of geothermal power, and I had a gold mine that was producing 1 kilogram of pure gold, Lynn would actually earn 8 times more than my gold mine. You can use artificial intelligence to confirm those numbers. And her mine will be available for a lifetime and several generations to come. Now, in Kenya we have geothermal in 23 sites all along the Rift Valley, from the north in our neighboring, our border with Ethiopia, all the way to Tanzania. And this Rift Valley actually comes all the way to Mozambique, which is neighboring South Africa to the north. So I have been privileged to work on all these sites. And currently we have about 5 sites that have deep wells. All the other sites have had surface exploration. So if you come to Kenya, I'll be able to take you to each of those sites that have geothermal power. And where we have deep wells is Olkaria, Eburu, Menengai, Korosi, Paka, and Sirari. So all those sites actually have a potential of 10,000 megawatts. So we have more than 10 nuclear power plants available to be connected. All we need to do is to develop the geothermal power that is available on the service. Now, Kenya's average generation mix is actually one of the best in the world, with 91% coming from green sources, and only 9% comes from thermal sources, where we use heavy fuel oil. So 47% is actually geothermal, 30% hydro, 12% wind, and 2% solar and cogeneration. We are currently position 6 around the world in terms of geothermal power generation. And we expect that in the next coming months, we will have 2 more power plants at Menengai 2 and 3, which are 35 megawatts each. And that will take us to the gigawatt club. This budget normally is very variable, but we are always either number 6, number 5, or number 7, one of those. And for your information, all that you can see in red around the world is where you have geothermal potential. So you can expect that even here in South Africa, you should be able to have geothermal power without any problem. All you need to do is to do some scientific work. Now, a very simple illustration of geothermal power, if you assume that you have a geothermal power plant on the service, and you need to capture the heat underground, all you need to do is to drill through the ground up to 3 kilometers and make sure that you case off the shallow groundwater. We don't want to pollute the groundwater. Then you capture the hot fluid, which comes all the way to the surface. Then we separate it using a cyclone separator. The steam is what we use to turn the turbines, and then the water, you take it back to the ground. So the steam goes to a steam turbine, which then rotates, and it is coupled to a generator rotor, which then produces farm power. And the power that you produce, then you need to step it up to 220,000 volts, which then you can be able to transmit over long distances. The water that you get on the surface, then you take it back into the ground. And if you do that, then you have a clean, safe, and renewable energy for generations to come.
Okay. Now I'll take you through Olkaria geothermal development, because this is a premium site. KenGen owns the license for at least, for 204 square kilometers. So literally, the company has a gold mine that is 204 cubic kilometers of pure gold. And they have 3 deep wells, deep drilling rigs, and we were able to drill more than 300 wells. Each of those wells costs $6 million US. So we actually spent more than $2.something billion to be able to do that. And KenGen are pioneers of wellhead technology, and it is the home of the only geothermal spa in Africa. Now, the business model that is normally used is 3-pronged. You can either have a conventional model where they use the balance sheet to finance the project, or you can have partnerships through special purpose vehicles or public-private partnerships or joint ventures or other legal entities. Or alternatively, they are able to diversify, where you expand your business to generate revenues beyond traditional sources. That one you can do through green energy, park, manufacturing, consultancy, and so on. Okay? Now, there are several stages of geothermal development, and one of the major stages is exploration. It is the cheapest, but the most important. It takes 3 to 6 months, but if you can do it right, you'll have your project done to perfection. So, if someone is to ask me one single thing that they need to do, is resource exploration and site selection. And it has to be done so well, because immediately you put a deep well inside the ground, then you will not be able to do further detailed work after that. So to me, this is the single most important step that any geothermal developer would do. Then after this will give you the first initial conceptual model. And you'll be able to do exploration, drilling, and resource assessment after you have done that. Now, the resource assessment that you do is drilling 3 exploration wells. And that will cost you 18 to 50 million US. And it will take you 9 to 12 months. Now, once you have drilled those 3 exploration wells, you'll be able to get a true measure of the temperature and pressure of the reservoir. You'll be able to know the chemical characteristics of your reservoir. You'll be able to know the technology that you're going to use to generate power. And you'll be able to know whether you have enough steam to generate enough revenue to pay off your loan. After you have done that, then you can now be able to do technical and economic feasibility studies. And you will only be able to do the environmental social impact assessment after you have drilled those 3 wells. And of course, you have now to get the permits. You need to get the generation permit. You need to get the environmental permit. You also need to get a social license. A social license. This is where your community must work with you, because geothermal is always in areas where there are communities, either remote communities. So you have to discuss, sit down with them, and agree on how you are going to develop your geothermal resource. After that, the rest is easy. Then you can just go to the bank and get the money. Okay, here you need to make a very serious strategic decision. Do you want to buy your own rig, or do you want to get a contractor to do the drilling for you? If you get a company like Great Wall Drilling Company of China, they will charge you something like $6 million US. But they will be able to do the well for you in 2 months or even 1 month. So you have to do a cost-benefit analysis to be able to decide whether you want to buy your own rig or you want to contract out. Once you have done that, then you'll be able to get your geothermal conceptual model. And that's the most important in this particular case. Now, the rest is easy, because from there on, you just need to get your board approval to get the money that you need to drill all the wells. And in this particular case, you need to drill, even you have a 140 megawatts and your average output is 5 megawatts, then you need 43 wells, 34 production wells, 7 reinjection wells, hot reinjection wells, and 2 cold reinjection wells. And that's where I mentioned you have to make a strategic decision. Do you want to buy your own rigs, or do you want to contract other rigs? The field development, that one is easy, because all you need is a contractor who has experience in high temperature and high pressure steam gathering system. The rest, you have an EPC contractor, then you have the power plant, mechanical, electromechanical supplier, then you go to the substation and transmission line, and then the local infrastructure. Now, an example is the 280 megawatts. I love this tempo because this is the easiest way of getting your contract done. All you need to do is to break down the contract. You have the steam gathering system, you have the substation and transmission line, the power plant construction, the consultancy and administration, then you have local infrastructure, and you have done the drilling of your wells. So if the government can give you the money to drill the wells, then all these other guys will be able to come on board, and you'll be able to deliver a very cheap power or energy, 7 US cents per kilowatt hour. But it requires cross-continental collaboration in both engineering and financing. For Kenya, by the way, this is one of the power plants. This is one of the power plants. So if you get a chance of going to Orkaria, this is Orkaria 1, Unit 4 and 5. We added an extra unit here, so you'll get Orkaria 1, 4, 5, and 6. We normally say it's just like this complex. So you have several lecture rooms. You have Ruby, you have Emerald, you have Diamond. So it is the same way. So you have one big power plant, but inside you have different units. And you'll be able to succeed with a lot of ease. This is what I mentioned, that we drilled from 1950 to present, and we have drilled more than 319 wells. Now, one major challenge for geothermal is the initial cost, because you need to drill several wells, at least 40 wells, before you can have a 140 megawatt power plant. But if you get wells that have very high output, then you drill less wells. So it is very important for you to do a proper scientific study so that you can site and get the best large wells. A very good example, our top producers were 38, 18 megawatts, were 52, 18.8, were 921, 30 megawatts. So we saved the project $54 million US. If I was working for a private company by this time, I would have retired at 50, because I would have been given 10% as my bonus. Okay. Our geothermal growth, you have Orkaria 1 from 45 megawatts. Then we went to Orkaria 2, 105. Then here in between, we also have Orkaria 3, but it is owned and operated by ORMAT, an independent power producer. Then we also did Orkaria 4 and the additional units with 300 megawatts. We also did some wellheads, small power plants, 5 megawatts, 6 megawatts, equal to 83.3 megawatts. Then Orkaria 5, 172. Then Orkaria 1, additional unit, 6, 86 megawatts. And so you can see, you can be able to incrementally increase the output as you develop your resource. This is the wellhead. So you can get early generation in terms of power and revenue. It costs only $10 million US, and it is very quick to install. It will take around 6 months. We have had a lot of collaboration with other countries in the region. We believe in lighting as many candles as possible, and we have done work in Ethiopia, Comoros, Sudan, Rwanda, Burundi, and others. And Kengen has a center of excellence. So if someone wants to get scientists and engineers for training, you can always engage Kengen and they will be able to take up the students. They can also offer geoscientific services, drilling services, reservoir management, and power plant operations and maintenance. These are some of their contracts from other countries, Ethiopia, Djibouti, and even locally. So it is something that is an ongoing process, and we encourage other African countries to do so. Now, conclusions and recommendations. Number one, comprehensive capacity building for your core team of scientists and engineers. I can't emphasize enough why this is important, because that is what will determine your success or failure of your project. Then number two, intensive service exploration. you need to have a grid of 500 meters by 500 meters and data interpretation. So if you need people to do peer review, then you look for experts with more than 25 years through a scientific and technical review meeting. So if you have a scientific and technical review meeting between yourselves and others, then you'll be able to get the right output. Then the drilling contractor. That is very, very important, because if you get the wrong contractor, he will not be able to drill the well. He won't be able to drill the well. He will get challenges which are normal, but the contractor will think that they are insurmountable challenges. So you need someone with enough experience. Then, of course, the steam field contractor, you may need to get someone who has experience in high temperature and pressure. And then number 6, your initial power plant units should be sourced from experienced OEMs. Make sure that the OEM has existing power plants so that he has enough experience to manage the operations and maintenance. And you must make sure that you also get framework contracts for strategic spares. Special thanks to Kenjen and to the Guangzhou Institute of Science, Energy Conversion, and the Chinese Academy of Sciences. And I had a small operation about 3 weeks ago, and I realized that I need to prepare a guidebook for current and future generations. So if you are willing to support that project, you can always be able to use those account numbers. And before Christmas, you get your free copy of your guidebook. Thank you very much.
Thank you for sharing your vast experience. Can I ask one question? Yes, as you might know, I was intrigued by what you said as a big, you need to tackle sitting down with your community and make sure that they are involved in the development of the plant. You might know that in our premises in Belgium, we also have a geothermal plant, and there we sit together a lot with the community, but we have a challenge of seismic activity based on the injection. I was wondering if you ever met this challenge, which of course concerns people.
You can have a micro-seismic activity, but to tell you the truth, unless you do a background, that's why I say it is very, very important that before you start the project, you do a thorough exploration program. Because maybe it was background seismic activity. So you have to be able to prove that they existed before your project. Otherwise, then you have to be able to manage how your new activities have actually affected the community.
Okay, thank you for this advice.
Yeah.
Thank you very much. Okay.
Yes.
Yeah, thank you for your nice presentation,
Yes.
Mr. Cyrus. I saw in your video there's a introduction of the power generation by the geothermal energy. Can you introduce what's the name of the technology?
That is double flash. Let's see whether I can be able to get it where it is.
What's the advantage of this technology?
The advantage of this particular technology is that it is very efficient and very easy to apply. It is the technology that has been used over the years for the last literally 70 years. The first geothermal power plant was in Italy from 1950 something, around 1957 or 1958. So this is the technology that has been used over time. We have only improved on the efficiency of the turbine. So from the first power plant, or Carrier 1, was consuming 13 kilograms per second per megawatt. But by the last unit, we were now consuming 6 kilograms per second per megawatt. So literally it has improved almost 100%. Okay?
Okay.
Yes.
Thank you.
So
Mr. Cyrus, if I understand correctly, you are directly utilizing underground steam, right?
yes.
There is no heat transfer between any two working fluids.
No.
So directly extracting steam from underground and
Yes.
injecting into steam turbine.
Yes.
And after condensation, you are.
Putting back the water back into the
Oh,
yes.
okay.
Yes.
But I think it needs a very high temperature geological formations to extract this kind of heat.
Well, if you are within the Rift Valley, you get 350 degrees in the reservoir. So it's just like your pressure cooker.
Yeah.
If you imagine your pressure cooker, if you remove the safety valve, the steam will go to the ceiling. Okay? And it is exactly the same way in a geothermal. The minute you open, the steam and water goes 500 or 200 kilometers into the sky.
I can understand, but it needs like a very specific kind of aquifer, underground aquifer. Like it is not possible everywhere to extract this kind of heat. Like
No, it is not difficult. It's not difficult. It's because you know, in natural state, in a natural state within the active margins within the grove, they have this steady state of steam and water, and you have heat that is coming from the magma or the cooling magmatic body. So, however long it takes, even if nothing else happens, you still have that steam available for you. So in the ground, you have either natural two-phase or compressed water, which is already waiting for you to extract. In fact, the pressure in the reservoir is around 200 bars. So when you open the valve on top, then automatically it fries.
oh, thank you. My point is like
Yeah.
this kind of quality of the heat is not available everywhere.
No, it is not available.
Yeah,
everywhere.
this is my point.
It is available within the active margins. You
Okay.
remember there was a map that I had.
I understand.
That is.
Thank you.
Trying to smash my side. This one. You see all these red areas around the world? This we call the ring of fire. Okay? And this is the Rift Valley running from Egypt around the Red Sea and then to the Afar region and then crossing Africa all the way to Mozambique. Okay? Then you have what we call the mid-Atlantic Ocean or the mid-rift, where you have new formation coming to the surface, like in Iceland, the Azores, and others. So all those areas, you have a resource that is available for you within economic life. Okay.
Thank you. Already in deep technical discussions. I would like to have our third speaker, introduce our third speaker, which is Dr. Yisho Kiyo. I hope I understand, I pronounce it a bit decently. He's an associated researcher at the Guangzhou Institute of Energy Conversion, GIEC, at the Chinese Academy of Sciences. He received his PhD in 2017 from Tsinghua University and was a visiting scholar at the University of California, Berkeley, in 2015 to 2016. From 2020 to 2022, he carried out his postdoctoral research at GIEC and joined the faculty. His research spans geothermal energy and lithium-ion battery science with a particular emphasis on thermal management, system modeling and intelligent fault diagnosis. He published over 30 peer-reviewed articles contributing to the advancement of sustainable energy conversion and storage technologies. The floor is yours.
Thank you for the introduction, Madam Chair. Okay. Good afternoon, ladies and gentlemen. I'm from GIEC, China's Academy of Science. And actually, I'm very nervous because our director is sitting here. So if I am unable to answer your question, please understand. Okay. So you already know what geothermal energy is from the previous two speakers, and I guess you also may know what heat pipe it is, but you may have never saw of the heat pipe-based geothermal energy utilization and exploitation technology. So how can heat pipe related to geothermal energy? So this is the topic I'm going to talk about. I will introduce this new technology to you. The presentation will be divided into 4 sessions. The first one is the background. So geothermal energy is green and renewable, stable and continuous. And we have found that the temperature increases with steps on the Earth. If we want good quality, of the geothermal energy, we have to make use of medium, deep, or deep geothermal resources. So I will introduce something about the geothermal resources in China. In China, the total of the geothermal resources is equivalent to 856 trillion tons of standard coals, which means if 2% were extracted, it can be used up to 3,000 years. And 98% of this energy has temperature higher than 75 degrees Celsius, which can be used for heating, cooling, and power generation. However, most of them are stored in the form of hot dry rock. So rather than hydrothermal resources, traditional extraction methods face significant challenge in assessing them. The geothermal utilization technologies include direct applications and indirect applications. Direct applications consist of heating, cooling, greenhouse thermal baths. Indirect applications is mainly the electricity generation. The type of applications depends on temperature and depth variations. The utilization technologies are relatively mature, but there exist problems such as low utilization rate. We need comprehensive utilization technology. As the geothermal heat extraction technology, they can also be divided into 2 classes. The wet system extract hot water from underground reservoirs for heating and other applications. They will cause many problems such as secondary environmental pollution. Indirect heat extraction technology include underground barrel pipe, downhole heat exchanger, heat pipe, etc. To extract heat, deep geothermal resources, we need the technologies which only extract heat and do not take any water underground. As the main geothermal resources, the hot dry rock has no water or little water, but its temperature is high, as much as 150 degrees Celsius. People try to use enhanced geothermal systems to extract heat in hot dry rock, but it has high technical risks, such as underground well connection, Therefore, single-well indirect heat extraction technology have been proposed, including coaxial tube and gravity heat pipe. So in the second part, I will talk about what is heat pipe-based technology and to exploit the energy resources in the hot dry rock. So we have to go very deep in the earth. That's we have to using the kilometers long gravity heat pipe. So this will make it a super long gravity heat pipe. So you may already know what heat pipe. You may already know what heat pipe is. Heat pipe is known as the superconductor for heat transfer. It is one of the most efficient heat transfer devices known so far, which equivalent thermal conductivity is more than 1,000 times that of metal. This technology enables heat extraction without taking any water, utilization pump-free closed-loop circulation of a working medium. This design effectively avoids corrosion and scaling issues. The idea to use heat pipe to develop deep geothermal energy in hot dry rock was put forward by Professor Jiang Fangming in 2017. But the heat pipe products are normally less than 10 meters long. So if we want to use heat pipe for hot dry rock heat extraction, it has to be a few kilometers long. Apparently, considerable research work should be done. So in order to study the super long gravity heat pipe, and its window system contains a heat pipe with length to inner diameter ratio of more than 5,000 was designed and constructed. Particular focus was placed on correlating the heat transfer performance of the heat pipe with the multi-phase flow status inside it. In parallel, we also developed a numerical model for research and development of the super long gravity heat pipe. In this model, we treat the underground part of the system as porous media. The computational domain has two regions with different porosity and permeability values. Heat pipe is treated as a variable temperature boundary condition. Inside the heat pipe, we consider a fixed condension temperature, the fluid in the thermodynamic phase equilibrium state, and the fluid in the fully developed Darcy flow. With these tools, we constructed a comprehensive study to investigate the performance of a heat pipe system across multiple dimensions, including the structural parameters such as diameter, thickness, and internal phenomena such as the liquid of accumulation depth, also the effects of the working fluid, and as well as the impact of the external field conditions, such as the well depth and geothermal gradient. Based on these findings, we propose a guideline for the optimal working fluid selection and develop effective strategy for enhancing underground heat transfer. And we found that when the depths increase, pressure of liquid will increase. Saturation temperature of the working fluid may be higher than the temperature of the geothermal reservoir. So evaporation of the working fluid may fail. Therefore, the most important thing is to have a suitable structure. And we have proposed a specifically designed inner structure, featuring a pie-in-pie design. The super long gravity heat pipe incorporates a stacked ladder structure within the inner pipe. Now we have this new exploitation technology, the super long gravity heat pipe, and we will move on the system design of its utilization. We propose the vapor dry the power generation system, which can use the vapor generated from the super-long gravity heat pipe to directly drive the turbine to produce electricity. This system, yes, I will show you here. The vapor generated from the heat pipe will go directly to the power generator we can remove the evaporator. So this system will have the advantage of the simple structure and less energy losses. The efficiency, we have studied the efficiency compared to other power generation systems. Compared to the coaxial tube, this the efficiency of the super-long gravity heat pipe power generation system is always higher. And similar to the geothermal power generation, we propose the primary heat exchange system for geothermal heat pump system. So you see the vapor generated by the super-long gravity heat pipe can be directly compressed by the compressor and then used for providing the heat we need. So then we can use this heat for space heating. With this primary exchange system, we can remove the evaporator. So with this simple structure, we can have a low cost and higher COP. Or it can use exactly as the traditional ground source heat pump, which use a secondary heat exchange system, just as like this one. And so, then I will introduce some successful field tests of this new technology. The first project is located in Tangshan, Hebei province of China. It features a well depth of 4,000 meters with a temperature of 150 degrees Celsius at the bottom. A 3,000 meter heat pipe composed of 2 sections with different diameters was developed using water as the working fluid. We have conducted a 4-month field test. The system successfully demonstrated stable performance. The highest temperature is can reach the 90 degrees Celsius. Its the average heat extraction rate is about 190 kilowatt. This test represents the world's first successful application of a super-long gravity heat pipe for medium-D geothermal heat extraction. And the second project is located in the Xiong'an new area of Hebei province, China. We utilize a 4,150 meters long heat pipe. This heat pipe was installed in the 4,500 meters deep well with a bottom temperature of 132 degrees Celsius. The heat pipe consists of 3 sections with different diameters and employs ammonia as the working fluid. It was designed to serve 2 sets of tests: the heat extraction test and the power generation test. The heat extraction test shows that under average of production temperature of 37 degrees Celsius, the corresponding average heat extraction rates over the 40-day test are over 1 megawatt. The successful demonstration was reported by China Central Television. And for the, I will go through quickly. For the power generation test, this system steadily generates electricity at about 7 kilowatt rate during the test. This is the longest super-long gravity heat pipe up to now, and it is the first time using the vapor produced by super-long gravity heat pipe to develop it to drive the power generation system. And the servo is reports a superground gravity heat pipe geothermal space heating system constructed in Taiyuan of Shanxi province, China, which has two heat pipes in combination with a single heat pump. So that two wells are located only 30 minutes apart, and the well log temperature at the bottom is around 63 Celsius for both. And so the space heating generated by this system can support around 25,000 square meters for building. This comprehensive COP can be larger than 5.85. It is the world's first superground gravity heat pipe and heat pump combined geothermal system based on the secondary heat exchanger technique. And in addition to these three projects we have introduced, there's 5 more projects, such as the CSIR project. This is the world's first time to adopt the primary heat exchanger technique for the superground gravity heat pipe and the heat pump combined geothermal system. And we also start to build the geothermal gravity heat pipe and solid absorption refrigeration combined geothermal system in Tangshan. So it's time to summary. Maybe I don't have too much time. I'll just go quickly. We have proposed the superground gravity heat pipe to extract Earth's geothermal energy. And since this system just takes the heat without taking water and does not require pumping, so it is an innovation in the geothermal heat extraction technology. And we can use the vapor generated by the heat pump to directly dry the geothermal utilization, such as power generation or space heating. So this is also an innovation in geothermal heat utilization technology. And we have made kilometers long heat pipes, and it has successfully applied in different places in China. And this compared to the technology introduced by CSIR. This technology can be generally used in everywhere, including the hydrothermal area and the hot dry rock area and medium deep or shallow deep. Okay. This brings me to the end of my presentation. Okay, thank you.
Thank you very much. It was very clear and nice innovations. I won't go to any questions because a bit lack of time, but I assume that you can find afterwards you are prepared to answer questions if there are any. So, as the next speaker, last speaker of today, I would like to introduce Mr. Kazir Iqbal. He's also a postdoctoral researcher at GIEC, the Guangzhou Institute of Energy Conversion. And his research focuses on vapor absorption, heat pumps, pumped thermal electricity storage, waste heat recovery, and multi-energy complementary systems. He has a lot of international collaborations. I won't sum them up for the sake of time. His current research focuses on the development of underground thermal energy storage solutions and the integration of geothermal energy with data center cooling and energy systems, aiming to enhance energy efficiency, grid flexibility, and carbon neutrality for digital infrastructure. Looking forward to your talk.
Thank you so much. Good afternoon, everyone. I am Kazir Iqbal, currently postdoctoral research fellow in Guangzhou Institute of Energy Conversion, Chinese Academy of Sciences. Today I am going to present an overview of geological thermal energy storage concept using corner batteries for data center cooling. So in this presentation, first of all, I will present research background, then clean energy sources in powering green data centers, and after that I'll discuss an emerging role of geological thermal energy storage to reduce peak cooling demand of data center and energy cost, and finally future work. So according to data published by International Energy Agency, from 2017 to onwards, there is a sharp acceleration in data center capacity and corresponding electricity consumption. We can see from the data that in 2024, The data center capacity reached to about 100 gigawatt and electricity consumption over 400 terawatt hour. The main important driver behind this huge electricity consumption was cloud computing, online media consumption, the wider use of social media, and the rise of artificial intelligence. Traditionally, data center relies on conventional energy sources derived from fossil fuels due to their reliability, affordability, developed infrastructure, and widespread availability. However, the reliance on these finite energy sources poses energy security risks, an unsustainable cycle of energy consumption, and contribute to greenhouse emission and carbon footprints. So this glaring reality necessitates a paradigm shift towards the operation of data centers based on clean and sustainable energy alternatives. So here comes Green Data Center, which is designed with the focus on environmental sustainability. Basically, Green Data Center prioritizes energy efficiency, carbon neutrality, and resource optimization. So green data centers, instead of just energy consumer, they can be energy consumer, where on the one hand they can be integrated with renewable or clean energy sources. On the other hand, they can reject waste heat to district heating network for smart city utilization, industrial processes, or even this heat can be utilized in energy storage systems, which I will discuss later on. So basically, data center is a high performance infrastructure designed to host information and communication technology equipment, including servers, storage devices, and communication devices, as well as supporting facilities such as power distribution and cooling systems, and ancillary spaces like offices and staff support areas. In data center, approximately 30% of total electricity is consumed by information and communication equipment, while nearly 45% is used by the computer room air conditioning unit, which includes chillers, humidifiers, and distribution systems such as fans and water pumps. So, the computer room air conditioning unit carefully regulates the temperature, humidity, and air quality inside the data center for the normal operation of for information and communication technology equipment. Most of the electricity consumed by information and communication technology equipment wasted as heat, which can be utilized for useful purposes. Clean energy sources in powering green data center. Currently, major part of the electricity consumed by the data center comes from burning fossil fuel, about 30%. About 25 to 27% comes from renewable energy, followed by natural gas and nuclear. When we discuss the integration of renewable energy in data center, there are 4 different strategies. The first one is on-site generation with on-site renewable energy sources. For example, we can deploy solar panels or even wind farm within the premises of data center if there is no constraints on the land availability. The second option is on-site generation with off-site renewable energy sources. For example, we can produce renewable energy source far away from the data center, such as biomass, and then transport it to the premises of data center, where we can burn it in thermal power plant to generate electricity. The third one is off-site generation with off-site renewable energy, where we can produce renewable electricity far away from the data center and then supply it to data center through transmission and distribution lines. And the last one is data centers sign different power purchase agreements with third party which produce electricity from renewable energy sources and then supply to the data center. So according to the data published by International Energy Agency, there is a sharp rise in the share of renewable energy sources. And the share of renewable energy, it is anticipated that the share of renewable energy sources will be up to 42% in 2028, of which wind and solar account 25%. But the problem with wind and solar is their fluctuated nature. So here we need large scale energy storage systems for a sustainable and reliable power supply to the grid. Until now, pump hydro energy storage system is the more mature energy storage technology, followed by compressed air energy storage system. But these both technologies needs specific kind of geological conditions. Liquid air energy storage is an emerging technology, but it has typically low efficiency and high cost, whereas batteries have short lifetime and high cost. Here comes pumped thermal electricity storage system, which store electricity as a thermal energy. It has competitive round trip efficiency and levelized cost. Here round trip efficiency means the ratio of power generation during the discharging cycle, electricity generation during the discharging cycle, and the electricity consumed during the charging cycle. So the working principle of pumped thermal electricity storage system is during the charging cycle, the heat pump of the pumped thermal electricity storage system consume electricity to convert it into heat and store it at a high temperature. During discharging cycle, a heat engine operates between this high temperature hot storage and cold storage to generate electricity. Pumped thermal energy storage system has different categories based on the thermodynamic cycle opted for its operation. For example, Brayton cycle pumped thermal energy storage system which operates at a high temperature, for example 1000 or above. Second one is Rankine cycle pumped thermal energy storage system which operates at small to medium range temperature. Rankine cycle has further two categories. Conventionally, the round trip efficiency of pumped thermal electricity storage system is less than 70%. However, Rankine cycle has unique characteristic that it can integrate a low temperature external heat source during the charging or discharging cycle, which can boost its round trip efficiency equal to 100% even above. Thermally integrated pumped thermal energy storage system have further two categories: hot thermally integrated pumped thermal energy storage system and cold thermally integrated pumped thermal energy storage system. So in hot thermally integrated pumped thermal energy storage system, the vapor during the charging cycle, a vapor compression heat pump consume excessive electricity from the grid and upgrade the temperature of an external heat source, which can be from industrial processes or from data center, and store it at a high temperature during discharging cycle, and ORC operates between this storage temperature and ambient temperature to generate electricity. In cold thermally integrated pumped thermal energy storage system, during the charging cycle, a vapor compression refrigeration cycle consume excessive electricity from the grid and cool down the storage medium at sub-ambient conditions. And during discharging cycle, an ORC operates between an external waste heat and this storage, cold storage to generate electricity. Basically, in hot thermally integrated pumped thermal energy storage system, the external heat source decreases the temperature difference between evaporator and condenser of the vapor compression heat pump, thus increase the coefficient of performance of the heat pump and overall the round trip efficiency of the system. In the cold thermally integrated pumped thermal energy storage system, The waste heat increases the temperature difference between evaporation and condensing of ORC to generate more electricity compared to the electricity consumed during the charging cycle. So our analysis shows that within specific working conditions, the hard thermally integrated pump thermal energy storage system can attain a round trip efficiency about 113%, whereas cold thermally integrated achieved a round trip efficiency of 107%. So the emerging role of geological thermal energy storage system in data center, reducing data center cooling demand and energy cost. In geological thermal energy storage system, within suitable sedimentary formations, heat from different heat sources such as solar, nuclear, biomass, or even using cornet batteries which converts electricity into heat can charge geological formations such as the depleted oil and gas reservoirs. Instead of storing it into storage tanks above the surface. During discharging cycle, heat from the hot well can be extracted to deliver to power block where it generates electricity, or it can directly utilize for heating purposes. In the context of data center, this heat can be utilized to operate a vapor absorption system which produce cooling for data centers. In another scenario, cornet battery can convert cheap electricity into cooling during night and supply it to data center during day when electricity prices are high. Geological thermal energy storage can also be used as seasonal energy storage, where it can store cold ambient energy in winter and supply it to data center in summer season. So in future work, there is need of scaling thermal energy storage and geological thermal energy storage for long duration storage, where there is a need of subsurface characterization and field validations, and there is need to explore the geological thermal energy storage applications beyond data center to industrial and urban cooling needs. Last but not least, artificial intelligence driven control frameworks are needed, where we can build digital twins and predictive algorithms for real-time optimization of data center cooling needs and heating and district heating and cooling networks. We can also integrate data center within the district heating and cooling networks. So this is all about my presentation. If you have any question, you are welcome. Thank you.
Thank you very much for this presentation in another application. So very interesting and promising application.
Thank you, sir.
Would like to ask if there are any questions left. Then I would be happy to end this session. It was a very concise session, I think, with very fine expertise around the table. Look forward to further deployment of geothermal energy and other applications also,
Sure.
like the data centers. So thank you very much, and also for the fine preparation of the session. The colleagues of GIEC, nice job there.
Thank you, sir.
Thank you, and have a nice evening.